Hello friends, here in this video we will see a problem in which we have to calculate the safe load. Here we have a question. I'll read the question and whatever is given here I'll write that in the form of data. Now here in this question the first thing which is given is an I section is to be used as a column having following dimensions. So we have an I section here and it has the following dimensions. Flanges are given, web and overall depth. Now if the flanges are given to us, we can write here first of all flanges 150 mm into 10 mm. Next, web is given 280 mm into 10 mm. Then the overall depth is 300 mm. Next, the column is hinged at one end and fixed at the other end, having length of 5 meter. So column is hinged at one end and fixed at other end, and it is having a length of 5 meter. So length of the column is 5 meter, that is 5000 mm. Calculate safe load by using both Euler's and Rankine's formula. So we have to find out the safe load, that is P suffix safe, by using both Euler's formula and Rankine's formula. It is given that take the values here: Young's modulus, compressive stress, Rankine's constant and factor of safety, which would be required in the calculation of safe load. So I'll write these values. Capital E, it is 2 into 10 raised to 5 Newton per mm square. Sigma C, 320 Newton per mm square. Rankine's constant 1 upon 7500 and factor of safety is given as 3. Now with the data available, let us try to get the solution to this problem. Now in this solution part, the first thing I'll do is draw the I section. Here I am drawing the diagram of the given I section. Now, here they have given an I section. So here we have material only in this section. Next, the dimensions are given. Flanges 150 mm into 10 mm. So we have top flange having 150 mm, its width and the depth is 10 mm. then even the bottom flange is having the same dimension, because here the dimension of the flanges are given together, no separate dimensions for top and bottom flange. So this is also having 150 mm into 10 mm area. Next, this central portion is called as a web, and for web the dimensions are 280 mm into 10 mm. So 280 mm is the depth of the web. This is 280 mm, the depth, and the width of the web is 10 mm. So here we complete the I section. Now after this it is given that the column is hinged at one end and fixed at the other end. So this I section, when it is used as a column, that column will be fixed at one end and hinged at the other end. And now here the length of the column is given as 5 meters, so that would be 5000 mm. And when the load is applied over this column, then it will start bending from the hinge portion, and bending will stop before the fixed end. So this much is the length which is subjected to bending, called as the effective length of column. So first we'll calculate this effective length. I'll say that since for one end hinged and other end fixed, effective length of column will be, effective length is equal to length of the column divided by √2, because this is the end fixity condition. Depending on the end connections, we have the formula of effective length. So therefore effective length will be, the length of the column is 5000 mm divided by √2. So here I get effective length as 3535.53 mm. So this is the effective length of column. Now after getting the effective length of column, I'll calculate the total area of this column. As we see here, if I divide this I section into 3 parts, here we have one rectangle at the bottom, other is at the top. So area of both the rectangles plus area of the third rectangle, which is the web. So I'll calculate the total area. Therefore cross-sectional area of given column, that will be capital A is equal to the area of one flange. Flange is having the area as 150 into 10. So like this we have 2 flanges. So 2 into 150 into 10 plus web is having area as 10 into 280. So the answer of capital A, it comes out to be 5800 mm square. This is the cross sectional area of the column. After getting the cross section area, in the problem they have asked us to calculate the safe load by using Euler's as well as Rankine's formula. First we'll start with Euler's formula. I'll say that since Euler's buckling load is given by P suffix E is equal to pi square E I minimum upon effective length square. I'll keep this as equation number 1. Now we have capital E and effective length. The only unknown is I minimum. So I minimum is the minimum moment of inertia, and if we look in this figure, we'll calculate the moment of inertia about x-axis, then about y, and whichever gives us the minimum value that we will select. Now how to get the moment of inertia about x-axis? Here what I'll do, I'll assume that from the complete rectangle, I'll explain it here. First, I'll say that we have a complete rectangle which will be having the width as 150 and total depth as 300. So 150 and 300, this will be B and here D value. So first we'll calculate the moment of inertia of this, and from this rectangle we will subtract two small rectangles, that is the rectangle here and the rectangle here. So once we subtract from the total rectangle moment of inertia formula the moment of inertia for these two small rectangles, we are going to get the moment of inertia for this I section in a very simple and easy way. So the width of this section is, total width is 150, this central portion is having dimension as 10, so this is 150 minus 10, so that is 140 divided by 2, so we have 70 here and 70 here. Then out of the total height, which is 300, this portion is 10 and even this portion is 10, so the remaining part is 280. So here we are going to find the moment of inertia. I'll write it onto the next page. Therefore mi for given I section, first about x-axis, Ix will be, as I have told, capital BD cube by 12, that is from the complete rectangle we are subtracting 2 into the smaller rectangle. Now the one small rectangle has width of 70 and its height is 280, so this is small BD cube by 12. Now putting the values here, capital B, the outer width is 150 into capital D, that is complete with depth is 300. So from this rectangle we are subtracting two small rectangles having width 70 and height is 280. 70 into 280 cube divided by 12. So from this I will get the answer of Ixx, and it is 81.4 into 10 raised to 6 mm raised to 4. Then I'll get Iyy. Now for Iyy, as we see this rectangle, we are dividing the I section into three rectangles: rectangle number 1, rectangle 2nd, rectangle 3rd, and for all three rectangles we have the same y-axis. So the formula will be db cube by 12 for first rectangle plus db cube by 12 for second rectangle plus db cube by 12 for third rectangle. So therefore Iyy will be D and B values. For first rectangle, D is 10, B is 150, so 10 into 150 cube by 12. For second rectangle, D is 280, B is 10, and for the third rectangle it is same as the first. D is 10, B is 150, 10 into 150 cube divided by 12. So here I'll get Iyy, answer is 5.648 into 10 raised to 6 mm raised to 4. So here in the Euler's formula we want I minimum value, that is the minimum moment of inertia. Now if we compare Ixx, Iyy, it is clear that Iyy value is less. It is 5.648 10 raised to 6, whereas Ixx was 81.4 10 raised to 6. So I'll say that since Ixx is greater than Iyy, so therefore I minimum is equal to Iyy, and the answer is 5.648 into 10 raised to 6 mm raised to 4. Now after getting this, I'll say that put all values in equation number 1. So we have in equation 1 Euler's load as pi square into E, and E value, it is given in the question as 2 into 10 raised to 5, to pi square into 2 into 10 raised to 5 into I minimum, which is 5.648 into 10 raised to 6 upon effective length square, effective length 3535.53 whole square. So from this I'll get the answer of Euler's load, which comes out to be 891.90 into 10 raised to 3 Newton, or 891.90 kilonewton. Now after getting the Euler's load in the problem, the question is to calculate safe load and factor of safety is 3. So after this I'll say that therefore safe load will be equal to Euler's load divided by FOS. So here we have Euler's load as 891.90 divided by 3. So therefore P suffix safe, that is safe load, comes out to be 297.3 kilonewton. So this is the first answer for us. That is, we have found out the safe load by using Euler's formula. The next thing is using Rankine's formula. So I'll say that by using Rankine's formula, Rankine's crippling load is given by P suffix R is equal to sigma C into capital A upon 1 plus small a upon effective length by K whole square. This is the Rankine formula. I'll give this as second equation. Now in this second equation, I'll calculate the denominator first and then bring the value, put it in equation number 2. So now for that I require K value as well, which is K square. So I'll say that therefore the radius of gyration which is K is equal to root of I minimum upon cross section area. So therefore K square will be I minimum upon cross section area. Now I minimum we have found out 5.648 into 10 raised to 6 upon the cross section area, which is 5800. So here I get K square value as 937.79 mm square. Now after getting K square, I'll calculate the denominator. So therefore 1 plus small a effective length square upon K square will be equal to 1 plus small a is 1 upon 7500 given. Effective length is 5. It is 3535.53 square divided by K square, which is 937.79. So I'll get the value of this constant, that is therefore 1 plus small a into effective length square upon K square. This term comes out to be 2.71. Now after getting this constant, I'll say that put all values in equation number 2. So we have the Rankine's crippling load as it was sigma C into capital A. Sigma C is given as 320 in the problem. Capital A is 5800 divided by The complete denominator we have found out, it is 2.71. So therefore the Rankine's crippling load, it comes out to be 687.87 into 10 raised to 3 Newton, or 687.87 kilonewton after I divide it by 1000. Now after getting the Rankine's crippling load, I can say that therefore safe load will be Rankine's crippling load divided by factor of safety. So it is 687.87. So now putting the values here, factor of safety was given as 3. So therefore safe load comes out to be 228.29 kilonewton. This is our second answer, that is P suffix safe or safe load. Now if we look into the question which was given to us, in that question they were telling us to calculate the safe load first by using Euler's formula that we have found out. It is 297.3 kilonewton, safe load by using Euler's formula. And then they were telling us to calculate the safe load by using Rankine's formula, and that we have found out 228.29 kilonewton. And once we get the safe load, we can say that because of the safe load the column will not bend, it will not buckle. So we have found out that safe load value, and with this we complete the problem.